So this is a reasonable choice. Okay? However, what it ignores is that some node, like this node 1 here and 2, they are pointing to many other nodes, not just node number 3. So think of a professor who writes reference letters for her students. And if this professor keeps writing that this is the very best student I have ever had in my 80 years of teaching at this university and so on, if every student she writes in that way, and she writes like, say, 100 letters every semester, then soon people will realize that, hey, this professor's reference letters should be discounted. And that's the idea here, is that you got to normalize by how you spread your importance score. If you point to too many web pages, then each of those web pages that you point to should not receive all your importance. And that is the idea that maybe I should look at the number of outgoing neighbors that I have. So if node 1 with importance score pi 1 points to 3 other web pages, okay, then O sub 1 equals 3, our degree is 3, and I should divide node 1's importance score pi 1 by O1. Okay. So I should be assigning just pi 1 over 3 to each of the 3 outgoing neighbors. And therefore, if you point to more nodes, each of them will uniformly receive pi 1 over, say, 5 instead of pi 1 over 3. And if you only point to one node, then that node receives all your importance score. So let's try number 2 now. Okay, the idea is that we're going to normalize by the spread of importance. It turns out that by this point, we're sort of close to what Google does. In the next 3 modules, we'll have to quantify this intuition and then provide 2 more enhancements. But we're getting there. Okay, the idea is that look at all the importance scores, add them up across the links pointing to you, but make sure you normalize by their outgoing number of links. Now you may wonder, if I have a node here, number 2 with importance score pi 2, I can write pi 2 as some combination of the importance scores normalized from the incoming neighbors. Now each of these, say this involves pi 1, can also be written as the summation of normalized importance scores from its incoming neighbors. So the question is, on the left hand side I will have pi 1, pi 2 and all the pi's. On the right hand side I also have all these pi's divided by their outgoing number of neighbors. So I got pi's both on the left hand side and right hand side of this, I guess, linear equation system. Can they actually make sense collectively? Is there a set of consistent scores pi? Is there a vector pi that can satisfy all these linear equations simultaneously? If so, then we have found a particular meaningful and self-consistent way to assign importance scores. If not, then we're in trouble. So the question now is, how can we modify this basic intuition in our try number 2 now in order to guarantee both the existence of such a set of consistent scores and an efficient way to compute these scores?